So I'll talk about eliciting expert judgments from groups of experts. It's joint work with these three other individuals here. So I've done a fair bit of elicitations over the last decade. I was trying to remember the projects where I've done some elicitations. So just to give you an idea of the sorts of contexts where these things are typically done. So these are quantitative judgments that usually getting probability distribution. So designing clinical trials. So for a sample size calculation for a clinical trial, you need estimates of things. Predicting drug efficacy. So in the UK, NICE decide whether drugs can be licensed and used in the NHS. They need estimates of long-term efficacy of drugs, and you don't have long-term data from clinical trials. So they use expert judgments there to predict student exam results. Climate change, so thinking about UK future electricity demand and how that's going to change as technology changes and how we use electricity changes under different potential scenarios in the future. Another climate change one, using a digital twin to look at resilience of infrastructure networks in the UK to extreme weather events like flooding and extreme heat scenarios, which are going to become more extreme over the coming decades. And then a lot of us have done expert judgment with EFSA, European Food Safety Authority. So looking at things like the likelihood of emerging food safety risks. And the Holly Food Project, which is the picture at the top, is an example of that one. And so within this context, eliciting a probability distribution for a quantity of interest, what's the total electricity demand in the UK going to be in 2040 in this particular scenario? In some sense, that's the easy bit. It's not easy, but we have pretty well-established and mature methods which have been used lots and lots of times for doing that. So just getting a single expert and getting their knowledge about something, their uncertainty about something, is relatively easy. Typically, if you're thinking about UK infrastructure planning for climate change, you probably don't just want to ask one expert. That's not going to be particularly reliable. And it's not going to be particularly well taken by people who are in charge. So typically what you do is you ask multiple experts to understand the range of opinion, the range of knowledge, the range of uncertainty on the quantities that you're interested in. And so then the question is, well, do you do what Jay talked about this earlier on in the day? And if I ask 9 experts, I just report their 9 probability distributions for electricity demand in the UK in 2040. Or do you somehow try and combine them or summarize them so that your decision maker isn't looking at lots of different probability curves and wondering what the hell they should do? And so a lot of the time, the brief that you're given from the decision maker is this one at the bottom. You've somehow got to summarize or combine them in a way that they can then parse them and use them to help make whatever decision it is they're trying to make. And so there's lots of different methods, there's lots of different protocols for how to do this. My view is that the gold standard is something called the Sheffield method, which is developed in Sheffield by Tony O'Hagan and Jeremy Oakley, a couple of statisticians in Sheffield. This is a consensus-based method. I'll talk about the diagram in a minute or two. So the idea behind the Sheffield elicitation is there's 2 stages. First of all, you get an individual probability distribution from each expert completely independently. So they don't talk to each other first on each quantity of interest. I'll talk a little bit about how you do that slightly later on in the talk. And then you reveal them. So if you've got 9 experts in the room, you reveal all 9 probability distributions and you get the group to have a chat. The group have a discussion about why they gave the judgments they did, what rationale they used, what evidence they used, what their experience is in this particular area, and how they brought that to bear on the problem. And then you do this second stage. You then have a group elicitation. And you try and go through the same process again to try and end up with a single probability distribution, which in some sense represents what the group thinks about the likely values and unlikely values of your quantity of interest. They're not suddenly all going to agree. They're all still going to have their own probability distributions. But what you ask them to do is you ask them to think, well, imagine there's a rational impartial observer, someone who's been sitting in the corner of the room. They didn't come in with your opinion or anyone else's opinion. They've seen all the judgments. They've listened to the arguments that have been made. What would they think? What would their probability distribution be for the quantity of interest? So this is what you're trying to elicit in the Sheffield method. The diagram at the top is the entire process of the Sheffield method. The only reason I put this up is to notice that these elicitation procedures isn't just go to an expert, ask them for their numbers. There's a whole process involved here, including collecting any quantitative evidence you have on your quantities of interest, making sure the experts understand and do some training with them, and really sort of going through a systematic process to do this. I don't have time to talk about that today, but there is a whole systematic process as well. Several projects I've worked on recently have said things like, and I don't agree with them or believe them, but they've insisted on this, we don't have time to get all the experts together, even in a Teams room. Experts are too busy. We couldn't possibly do that. Another project said, well, if you get all the experts in a room together, the loudest voices dominate and you don't get a true sense of the judgments of the experts, or they all defer to the most senior person in the room. Now, I've done lots of these things and I don't think any of that's true. Medicine in particular, I think that the top clinicians are just too busy to do this and couldn't possibly do this. Again, I don't think they're more important than the top people in nuclear safety, but you know, this is a sort of widely held opinion. So in recent times, I've not always been able to do the Sheffield method. So there are some alternatives that I think are reasonable. That if you couldn't possibly get the experts in a room together, you couldn't possibly do the Sheffield method, maybe here's something else you could do. So one is called the probabilistic Delphi method. So this is based on something that you might have heard of, the Delphi method, which is usually for eliciting sort of preferences or rankings of things, so something not quite probability distributions. But just like that, when you have several rounds of individual elicitation. So here's my 3 experts here. I ask them at different rounds for their probability judgments. So I ask them for their probability distributions at different rounds. And then in between the rounds, we have some anonymized information sharing. So that's sort of what this part is here. So I reveal to all 3 experts the probability distributions of each other. I don't say whose is whose. I also get them to talk about why. So there's a rationale that goes with each probability curve. So each expert sees what everyone else said and what they ended up giving them in terms of probability distributions. And the idea is over subsequent rounds, the experts begin to come closer together in their judgments as they consider the arguments made by others, and perhaps they understand the question a little bit better. Then the diversity in the probability distributions, the differences between them gradually gets less and less over time. Now, there's conflicting evidence as to whether that actually happens. Another one I want to mention is something called the IDEA protocol. This is similar to the probabilistic Delphi method. In this case, you do some individual elicitations followed by a discussion. So it's very like the Sheffield method. So again, you've got to get the experts together for this one. But then instead of doing the consensus step, which again, there's reasons why sort of psychologically some people don't like this one, you just do a second round of individual elicitation. So you sort of got round 1 and round 2, like the Delphi method here. But then in both of these methods, there's a question at the end. I've got 3 experts. I've got 3 different probability distributions. I wanted 1. What do I do? And so in both of them, they say you should use a mathematical rule for consensus. For probabilistic Delphi method, they say, well, they're all experts. Weight them all equally. Just take an equally weighted average of all the distributions of all the experts. In IDEA, what they usually do is something called performance-based weighting. You test your experts. You ask them some questions that you know the answer to, but they don't. You get their probability distributions and you see how well they do. And the ones that do well on the test questions, they tend to call them seed questions, get higher weight for the questions that you don't know the answer to, the ones you're actually interested in. So that's performance-based weighting. Now, I don't like either of these suggestions. I don't think they're the right thing to do. So is there anything else you could do? I'd really like them to come to consensus, but let's suppose I can't. Let's suppose I can't get my experts together. I can't get them to come to consensus. What can I do? Well, there's an idea that's been around for a long time called, well, I like the phrase Bayesian reconciliation. It's also called Bayesian aggregation. It's been around for longer than me. So it's been around since 1977. And this is an alternative. So this says use Bayes' theorem to combine the probability distributions from the experts. So I'll talk through why that might be sensible as we go through. So the idea, the standard way to elicit a probability distribution from experts is to ask them essentially for their best guess. The median is what you normally take that as. You define it properly and you train the experts properly, but you get a best guess, a central estimate from the expert, a median, which I'm calling M here, and you get a sort of interval of plausible values for the quantity of interest. So L would be some quantile below the median, so the lower limit of plausible values from the expert, and U would be the upper plausible value. So they think it's probably going to lie between L and U. Their best guess is M, is one way of thinking about these.
you define them formally when you do it. For some quantity you're interested in eliciting, theta. And in Bayesian reconciliation, you treat the expert judgments as data. So all these L's, M's, and U's from my different experts indexed by I, we treat as data. And we imagine there's an extra person. And so when Jay was talking that Bayesian analysis has to be for a particular person, in the first talk, we think about this extra person in Bayesian reconciliation who we call the decision maker. Now, this could be an actual person, or it could be a synthetic person that I've made up in order to be able to combine my expert judgments. But the idea here is your reconciled distribution is going to be what they think, having heard what all the experts have said. So you start off with what they thought before all the experts gave their opinions. That's their prior distribution, pi of theta here. And then you have what the experts think, which is represented by this F term here, which is the likelihood function for the lower quantiles, the medians, and the upper quantiles, the experts. Given what this thing is, you multiply them together, that's Bayes' theorem, as we saw slightly earlier on. And what you end up with is the posterior distribution, which is the decision maker's distribution for this quantity theta that's still unknown, given all of the information given you by the experts, given what each of the experts think. So now somebody owns this combination of all the experts' distributions. That person is the decision maker. How do you define the prior for the decision maker? Well, either you set it to be sort of quite non-informative, because if the decision maker was an expert, they would have been included in the experts. Or you actually ask your decision maker, you perform the elicitation with the decision maker as well. And so then you can carry that process out formally. The nice thing about doing this, rather than just taking some sort of weighted average, is that you've actually got an interpretation of what results as a subjective probability distribution. It's the prior distribution of the decision maker. It's the decision maker's distribution in light of what the experts have said. The other nice thing is it gives you some flexibility. The other methods sort of assume that each expert is giving you independent judgments from every other expert, but they might have been educated at the same place. They might have been employed by the same company. They might have had similar experiences throughout their career. They're probably giving you judgments based on experience which are correlated with one another, which are dependent. So typically, it's not reasonable to assume that experts are giving independent information for one another. And by structuring this likelihood term, you can take that into account when you do your Bayesian reconciliation. There's only 3 slides with formulas, and that was the first one. However, the next 2 are the 2 that have the rest of the formulas. So there's different ways of doing this. Recently, people have proposed to do this using hierarchical modeling, this reconciliation, this Bayesian model that I outlined on the previous slide there. I'm just going to give you a little bit of an example of how this might work over the next 2 slides. Don't worry if the details aren't amazingly clear straight away if you're not an enthusiastic Bayesian statistician like me. So suppose we've got experts, they're I in a group, subscript G, for some quantity theta that we're eliciting, and from each of them we've got this plausible range of values in their central estimate. The reason we group the experts is to take into account these dependencies. So what we do is we look at our group of experts and we say, these are all particular types of toxicologists. They're going to give me similar views, whereas these come from a different field. They're going to give me similar views to each other, but slightly more different views from the toxicologists. So you can group your experts based on that. Or if you go through the probabilistic Delphi method, you've got the rationales from the experts. You could say they're relying on the same evidence. They're going through the same thought process. So you can group your experts, and experts within a group are giving you more dependent information than experts that are in different groups. And then we propose a hierarchical model for each of the pieces of information that the experts have given us. So here's an example. So the median for expert I in group G, we say at the first level of the hierarchy, all of these experts within a group come from the same normal distribution with some mean for the group and some variance for the group. And then you have a group level. So the mean for the group level then just comes from some overall normal distribution. And then the mean from this overall normal distribution, this is what your decision maker thinks before they see the expert's judgments. And so that's how you incorporate the prior knowledge. And so the idea here is by defining this hierarchical structure, all of the expert judgments are correlated, but expert judgments within a group are more correlated than expert judgments between groups.
And you can do the same for the lower and upper plausible values, except L has to be below M and M has to be below U. And if you do it all independently, that might not be true. And so instead, you can do it on the differences. So the difference between the median and the lower, and the difference between the upper and the median. But that's just a technical detail. It's all the same idea. And then your reconciled distribution is just the one at the very bottom level. So once you've performed inference and estimated all these parameters, your reconciled distribution for the median is the posterior distribution for that mu term at the bottom level there. Okay. Details I don't really have time for. So essentially now we need some sort of distribution for theta that's flexible enough to represent anything that the expert might think. And so we just want a flexible distribution that can satisfy whatever L is, whatever M is, and whatever U is. So 3 parameters would be useful because we're specifying 3 things. So here's a 3-parameter distribution. And the nice thing about this one is you can do some algebra and you can get any quantile of this distribution in terms of these 3 parameters. So if I've got a U, an M, and an L for a particular expert, I can rearrange this formula so I can write U is equal to something in terms of these 3 parameters, L is equal to something, and M is equal to something else. So I can work backwards and forwards between them easily. So this is my favorite flexible 3-parameter distribution. So we can solve for the parameters in closed form if I've got 3 quantiles from a particular expert. And therefore, if I can sample these quantiles from my hierarchical model, from my posterior distribution, from my hierarchical model, from my for my decision maker, then I can get samples from the quantity of interest just by plugging them into that distribution there. So I said that Bayesian reconciliation is nice because you've got this nice interpretation that it's the decision maker's posterior distribution. That isn't quite true with these hierarchical models. They don't quite satisfy Bayes' theorem that I showed you 2 slides ago. So we have a slightly different interpretation here. So what we're actually doing here is we're supposing there's an underlying distribution which represents the agreement of the expert. So that has to be true for this to be a sensible thing to do. And so what these hierarchical models are actually trying to do, they're trying to learn this distribution, what the agreement of the experts would be if there was such a distribution. So in the last couple of minutes, I'm going to go through an example. So now there's pictures and no more equations, I promise. So this was an elicitation project to identify a cost-effective means of early detection of progressive internal erosion in embankment dams. So there's an embankment dam. The idea was to manage erosion of this project. So the idea was there was going to be an inspection schedule for these dams, and they wanted to work out which ones to inspect and in what order. And so they wanted to expect the ones that they thought might not be, that might need some action. So in the dam study, there were 11 experts, and they naturally fell into 3 groups. Some were employed by the people doing the study, some were academics, and some were other industrial consultants who weren't employed by the company doing the study. And they asked the experts 11 of these seed questions that we know the answer to, but the experts didn't. So we can use this data set to explore what the method works, how the method works. The way they did this, so they asked for an M, a median, and they asked for lower and upper quantiles, which they asked for the 5% and 95%. So they essentially got a 90% interval estimate on each of the quantities of interest from the experts. And originally, this was done using performance weighting. So we're comparing our method of the performance weighting here. So using our Bayesian reconciliation, I fit that model that I discussed. These are the 11 seed questions. So there's 11 vertical bars here. The red crosses are the true values of the seed variables. And these are our decision maker prior distributions. So these are our reconciled distributions. The blue dots are the medians of those distributions, and the length of the intervals of the 90% uncertainty intervals. So what you can see is by using our method, the true value is always just about within the 90% intervals. So it should be within the 9 out of the 10, about 9 or 10 of the times. 11 is not too bad. And sometimes it's above the median, sometimes it's below the median. So it looks like it's sort of, we've got something which is reasonably well calibrated here.
But is that just because we had 11 really good experts and we've just combined 11 really good things to get a really good thing? No, the experts are terrible. So here's the 11 seed questions. The different colors are the different groups of the experts. So if they're the same color, they're in the same group. The horizontal dashed lines are the true values of each of the seed variables. And again, the points are the central estimates from the experts and 90% intervals. And what you'll notice, I know these are small, what you'll notice is that the vast majority of the time, the true value is not within the experts' 90% interval for any of the experts. And this is true in almost all expert judgment studies. Experts are consistently incredibly confident and give far too narrow intervals. So what this Bayesian reconciliation method does, and so the Bayesian reconciliation is the blue one on the very far right of each plot. It essentially gives credence to everything that an expert gave credence to. So it sort of pulls out the distribution. And so it counteracts this overconfidence from individual experts, essentially. And that's why it's doing quite well in this particular example. Okay. Does it just do well on this example? I'm running out of time, so I'll go quickly. We have 45 studies like the one I just showed you where we've got variables that we know the answer to. So I've essentially run this method for all 45 studies, and I've compared it firstly to equal weights, so just giving equal weights to each expert. Secondly, to just randomly selecting an expert and saying use that expert, so we don't have a group. And third, on this one on the x-axis, something called the classical method. This is this performance weighting approach, where they decide which is the best combination of experts to use. So on each plot, there's a cross for each study. The red line is the y equals x line. Any point above the line, our method does better than that method. Any point below the line, the other method does better than our method. So based on these 45 studies, which is the only database that I'm aware of that looks into this, we do better more than half the time compared to any other method that we've seen. And that, yeah, that's what that says as well. Okay. I'd like to do the Sheffield method. I can't always. There are some other methods out there, but they make you choose a mathematical rule to combine the judgments of the experts. I think this is a better approach than anything else that's been suggested so far. And that's that.